Good morning. So today we're going to do a lab, but unlike most of our labs, we're actually going to do the analysis first, and then we're going to carry out the lab, and you'll see why in a moment. First, let's take a look at a warm-up problem that'll help us make clear some of the things we should have learned yesterday. So we're going to assume that Astros outfielder Michael Brantley has thrown a ball up at an angle, and it follows the path shown below. And what I want you to do is to identify the direction of the horizontal velocity and the vertical velocity at each point in this trajectory that I have labeled, and also tell me the direction of the acceleration at each of the points, and then tell me the direction of the total velocity. So go ahead and pause the video for a moment, discuss that with your neighbors, and then restart the video once you think you have an answer. So what we can do is, let's do the horizontal velocities first, because that's the easy part. As we saw yesterday, the horizontal motion is not affected by the vertical acceleration of gravity. Therefore, the horizontal motion should be constant velocity. So we should expect to see the horizontal velocity staying the same throughout the whole entire trajectory. Now the vertical velocity is just like free fall. So initially the vertical velocity is in the upward direction, but then it gets smaller, and at the very top of the motion it is no longer going up any higher. That's what makes it the top of the motion. So there's no vertical velocity, and then it starts getting larger again, but now in the downward direction, and then it gets larger still. Now the direction of the acceleration is easy, because there only is one acceleration. It is the acceleration in the vertical direction, and that always points straight down. So I'm not even going to draw it here on this little diagram. As for the direction of the total velocity at each point, well, you can just mentally take the sum of the horizontal and vertical velocities. You have to put them tip to tail and imagine which way they're going to point. And what you should find, if the velocities were drawn correctly to scale, which they're not, is that the velocity points along the trajectory, tangent to the trajectory at each point. Okay, so let's talk about the problem that we're going to do today. It's going to be a horizontally launched projectile. A ball is going to roll off the table and onto the floor. So let me show you the system we have set up. I'm going to show you in a video, and then we'll come back to the PowerPoint in a little bit. So this is the apparatus we're going to use in this experiment. We have here two photo gates, and they are attached to our LabQuest unit, and we have a ramp made from a lab stand and a claw clamp and a piece of molding. Now a photo gate is just basically a arch that has on one side an infrared laser and on the other side a detector. So when the laser is blocked, the photo gate sends a signal to the LabQuest unit telling us that it's blocked. And so when you block it, as I'm going to do here now, I'm going to block the first photo gate, and it senses that it's blocked, and then I'm going to block the second photo gate, unblock the first, and it says the second one is blocked. So because we have those two photo gates over there, the way it works is when we roll the golf ball through the photo gates, by timing how long it takes the golf ball to get from one photo gate to the other, the LabQuest unit can tell us what the velocity of the golf ball was when it rolled through there. Let me show you how to set up the photo gates in order to know what the time was for the golf ball to roll between one and the other. We want to have it to be under photo gate timing and pulse. So over here on the right hand side where it says mode, we're going to change mode to photo gate timing if it is not already that. And then the photo gate mode is going to be pulse. It's a little drop down menu. We're going to choose pulse. And then where it says distance between the gates, we're going to pick 0.1 meters if that's indeed what we have. We need to measure it, and if it's 11 centimeters, we'd say 0.11. And then we're going to say OK. Okay, so we're all set up and ready to go here. What we're going to do is some trial runs where we figure out what the velocity of the golf ball is, and then we're going to do the actual run where we let the golf ball hit the ground. In all the trial runs, it's important that you don't let the golf ball hit the ground because that would be cheating. We want to predict where the golf ball is going to hit, place our target there, and then see if it actually hits there. So each time you roll the golf ball down before your actual final trial, you need to have somebody over there catching the golf ball so that it doesn't hit the ground at all. So in fact, have them catch it right as soon as it leaves the table so that you don't have any idea where the golf ball is going to land just from looking at it. So when we're ready to start doing our practice runs, we can press on this button right here. That's like our start button. If it asks us this message, we can just discard any data that's already on the device. Okay, so we'll put the golf ball here. I mark a certain position that I know I'm going to launch the golf ball from that same position each time. And now we're ready to go. And it actually did record on the graph the pulse time and the velocity, and also has it over here on the side as the pulse time and velocity. Okay, so now we have one measure of velocity. We're going to go ahead and do it again. So put the golf ball back in the same position. To do a second run, we just go ahead, we don't have to restart it, we just go ahead and start the second golf ball rolling down. This one hit the side a little bit, so it might be a little bit different. And if you notice that it's significantly different, you might want to be careful. You might want to do some runs over again. You want to get consistent velocity as the ball rolls off the table. You can do that 3 or 4 times, just enough so that you get a consistent measurement of the velocity of the golf ball as it goes between the 2 photo gates. And then you'll be ready to do your actual trial. So we're going to get our target ready. This is after we've done all of our calculations. We will take a target here. This target is just a New York Yankees logo. I'm going to have a different logo for you all when you do this lab, depending on who the Astros are playing that week. And we'll put a piece of carbon paper on top of the target. You'll notice, by the way, the target, it does have a ellipse drawn around it here. So if you get within the center circle, you get so many points, and if you get around the ellipse, you get so many points. We'll figure that out later. But the point is, you'll notice it's an ellipse on a circle, so it might make a difference in how you place your target. But you're going to put the carbon paper on top of it, and you'll see why that is in just a minute there. And I'm just going to place it some random spot I think is approximately where the golf ball is going to hit. I have not yet done the calculations for this table. Okay, then I'll do my actual run here. This is the final one. And what you see here is a little mark right here. The other marks where I did trial runs when I was making this video. But this mark right here is where the golf ball actually hit. And a little carbon paper just made the imprint on this target. So you would turn in your calculations and you would turn in this target, and from that we will base your grade on this lab. Okay, so we're trying to make a horizontally launched projectile. Horizontally launched means that the initial velocity is entirely in the horizontal direction. There is no initial vertical velocity. So V naught y is equal to 0. And here is the situation from the apparatus I just showed you. You have this ball rolling down a ramp, and it's going to go between the 2 photo gates. This particular table is 0.86 meters high. Let's see what happens. Well, the ball rolled off the table and onto the floor. After it left the table, it becomes a projectile because the only thing acting on the ball is gravity. So let us try to solve the problem of how far away from the base of the table will the ball go before it hits the ground. And we're going to use the gummies method for problem solving. And hopefully by now I have introduced the gummies method of problem solving, but if not, you'll get the idea as we go along. Gummies stands for givens, unknown, model, method, implement, and evaluate the solution. So the first thing we're going to do is going to write down the information that we have been given by our problem. We know that the vertical initial position is 0.86 meters. Let's let the 0 position in the vertical direction be the floor. So the initial position in the vertical direction will be 0.86 meters, because that's how tall my table is. And the final vertical position will be 0 meters. We know the initial vertical velocity is 0 because the ball is rolling in the horizontal direction when it leaves the table, so it is not being launched vertically at all. We know there's no acceleration in the x direction. We're going to ignore anything like air resistance that might cause the ball to slow in the horizontal direction. And we know in the vertical direction the acceleration is, well, the worldwide average is a negative 9.81 meters per second squared. So the question we have to ask ourselves, the unknown, the U in gummies, is how fast is the ball rolling when it moves off the table? And then how far will the ball go from the base of the table? We'll call that Vx and delta x. The model here, well, we have two kinds of motion. We have horizontal and vertical motion at the same time. So the horizontally launched projectile will have a constant velocity in the x motion. We'll use the constant velocity model there, and the y motion will be constant acceleration. So take a look at this screen, make sure you understand everything here before you move on. Go ahead and pause the video if you need to. All right, next, after we settled on our models, givens, unknowns, and models, we need to come up with a method. That means we need to know what parts of our model are we going to use to solve our problem. Well, we're going to use those photogates, as I demonstrated in the live video, to find the initial horizontal velocity. In fact, the LabQuest unit actually gives us the initial horizontal velocity. But if it didn't, if it just gave us the time interval between the two photogates, we could just take the distance between the two photogates and divide it by the time interval to get the initial horizontal velocity. Now, since we know the horizontal velocity, all we need to do to find the distance that the ball goes horizontally is to find the time of flight. So we can use our vertical information to find the time of flight. We'll use this equation. And then once we have the time of flight, we can plug that into the constant velocity equation in the horizontal direction, and that should give us our distance. This was, as I said, the way that we would get the velocity of our ball when it was rolling off the table right before it starts to leave the table. So we are going to solve for the time of the fall by using the y equation, as we said. This simplifies a little bit because there is no initial vertical velocity, so it just becomes 0. The final position is equal to the initial position plus 1/2 at squared. And we're going to solve this for t squared. We always solve our equations before we plug in numbers first. And that gives us, after we solve it, it's a 2 times a negative y naught over a is equal to t squared. Substituting now a negative 0.86 meters for y naught and a negative 9.81 meters per second squared for a gives us that t squared is equal to 0.1753, which means that t is the square root of that number, so it would be 0.42 seconds. Now we know the time, so we can find the horizontal displacement from that. We just take our horizontal velocity, multiply it by 0.419. Okay, so now you're ready to do your trials. Go to your lab stations and do your practice runs without letting the ball hit the ground, and then locate the target where you think the ball is going to land, and do your actual trial and write it up and turn it in.